I have already gone through the brute force approach, in which we have seen that how we can implement this one, right? And this code I have already gone through, right? So as you can see that what I have to do, we have to do that we will move I plus 1 means a step 1 and a step 2, right? A step 1 and a step 2, because we can either climb one or two step, right? We can either climb step 1 or step 2, and so that we have to climb one way, right? So if it is saying if we have n equal to what, 2 step, right? If n equal to 2 step, it means what, we have a stairs that we can move like this, right? This is the stairs, right? So if person is here, right? If person is here and he want to reach to here, right? And he want to reach to here, so how he can move there, right? So the he can move by a step 1, right? S1, and then he will move from here to here, right? In S2. So in by using one step he will reach there. This is the one way, right? And he can jump from here to here by another step, right? That is called 2 step, right? 2s, and he will reach here. So maximum is what, maximum 2 ways he can reach, and that's why we will returning here as a 2, right? As output, so that we have taken one step for this one I plus 1, right? How many ways he can reach there, and another we were returning I plus 2, like how many ways. For this one we are doing this one, and for this step we are doing this one, right? And the base case was what, I is greater than n, means what, I step 1, if that is greater than equal to n, right? Greater than n means we have I some value that we are at what position, some position. Let's see, initially we are at ground, so it is 0. But if I is already at 2, means that is already on top, he is not on the ground, he is on the top, it means it is on the ground, right? And it is on the top, correct? So if I value is already 2, and so that it is saying if it is greater than n, and if I is going to 3, means more than top, it means what, we do not need to climb anywhere, correct? We do not need to climb. That is our base case. So another base case was what, I equal to n, in which what we have to do, means if that is equal to top, right? Equal to top, so he can maximum move to what, the one position only, I equal to 1. So these are two base cases that we have to talk about, right? And we have gone through that. So test cases always, sorry, base cases always take care. The first, if I is greater than n, and second, I equal to n. So when I is greater than 0, means we have to take return as a 0, and if I equal to n, it means what, we have to return 1, right? These two. And the recursive function that will you have to return, and that will call this recursive function, right? So I think you have understood already this climbing stairs. And so this was our brute force approach, and we have seen that the climbing value will get only through I plus 1 and I plus 2 steps, right? So this was our base case. We are returning 0 if I is greater than equal to n, greater than n, and if equal to n, means we have returned n. And then we will do for the step 1 and for step 2. So total ways we will get from here, total sum we will return from here, plus total sum of return will here. So total count we will get from the step 1 and step 2, and we will return finally in here for the output, in which we have to take care two base cases. Base case is 1 and base case is 2, correct? So this is your brute force approach. Now we'll see that the complexity, right? What complexity we have? Complexity is O of 2n. Why? Because the size of recursion will be 2n. Let's see, if I is what, I is n equal to 5, right? If I is n equal to 5, so we'll see that what, sorry, go back. So what happened, if we will take n equal to what, 5, right? N equal to 5. So what we have to do, this initially it will be 0 n, right? So either he can go a step, one step, right? One step he can go, or either he can go two steps, right? So if he is going in the way in which he has to go with the one step, right? So in one step, how many ways? Sorry, in one step there is only two ways: one step and two step. So one, when he is choosing the one step way, so how many nodes he will to traverse, right? So he will start from 0 to 1, feed 1 to 2 and 3, right? Feed he will go to 3 and 4, feed like that. As similarly, why? Because the first time when he will take one step, right, he will take, now he has, this node can also go either one step or two step, right? Now when he came to this step, he can go one step or two step, 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 one step and two step, right? Similarly, if he is at this position, right, he can go one step, two step, one step, two step, one step, two step, one step, two step, right? Like he can reach, he can move to any one step or two step, right? So these are the possibility in which we can see that total number of nodes is what? O of 2n. Why? Because if you count this this one, right, the 2 to the power n is what? 2 to the power 5. It means it is 32, right? Total node we have 32, and that's why we are saying that the complexity, because we have to move to all the nodes, right? And so that the time complexity will O of to the power n, right? And that is our time complexity. But space remains same because we have to move the what we can say that depth till depth n, right? Only n. Not we are moving n equal to 5, right? As you can see that in all steps you can see n is remain maximum 5, right? And so the depth of the recursion tree can go up to maximum 5, and so that space complexity will remain O of n. So this was our brute force. Now we will see that this is approach 2 in which we will see that recursion with the memorization, right? So this is the approach in which we will talk about how we will implement memorizations, right? So in the previous approach we are redundantly calculating the result for every steps. Instead we can store the result at each step in the memorization array and directly returning the result from the memo array whenever the function is called again. So in this way we are pruning a recursion tree with the help of memorization array, right? And reducing the size of the recursion tree up to n, right? So let's understand the recursion. So what we will do that first, we are using memorization, right? So we will take a memorization memory as an array, right? And so that we are taking array of size n plus 1, right? So n is the number of steps we have to move at the top, but we'll take n plus 1 as a maximum index, you can say that, right? Size. And we have a function climb stair, like in which we will pass 0 and memorization, right? Only this extra we are passing, like from the previous one we are adding this one. So only memory will pass, rest of the cases will remain same. Case 1, base case 1, base case 2, and this we have to see if memo of I is greater than 0, right? Then we will return what? Memo of I. If memo at I memorize, like already we have calculated, right? And that is greater than 0 means we do not need to calculate, we have already stored, right? Because if array contains, this is the index, let's say this is the I index, okay? I index, let's say 0, and we have 20, right? So we do not need to calculate again for this index, because if we will move to here, right, if the calculation is happening, if we store this one, right, at some place, if we store some this one at some place, right, so the array is already counting, array is already have 0 at 1. So next time when we will come here, so if we'll see that here 3 5 is already there, 2 5 is already there, right? So when we call about 2 5, right, this one, so it is when the second time it will come, it is already stored here at the time here, right? When we come here, right, 3 4, so you can see that 3 4 is already calculated, correct? Let me do again, okay? So if we are talking about the 0 5, right, so we are going toward one step, then we have to what we have 1 5. Here what we have, we are going 2 steps, so we have 2 5, correct. But first this one, if we are taking one step counting, right, so we will move only this step, right. So 2 5 is already here, right, and now 3 5 is already here. So once we have traversed this node, right, the memory we are storing data here, right. How we will store? We will take, that is m of I, and we'll store what, 2 5 data is already there. Okay, 2 5 data is already there. So when second time we'll come here, we'll see that we have already calculated for this node here, right. So we do not need to calculate here because we have already calculated here. Similarly, if we'll move to here, that we will get what, 3 5, right, and that's we have already calculated and we have stored on the memory. So here we do not need to calculate, and here will be what, 2 5. So if we will move here, you can see that 4 comma 5, this is already done here, so no need to calculate here. It means this is the benefit of memorization, right. So now we will do what we are doing actually, where we are saving the data on the memory. Here we have I plus 1, I plus 2, and we are passing memory, and we are storing the value at memo, right. The sum we are calculating I plus 1 or I plus 2, that for the particular node, right, the particular node. So the particular node value is already at what, memo of I, and we are returning what, memo of I. And that's why when memo of I is here, when memo of I is already greater than 0, means we have already stored previously and we do not need to calculate, right. So we will return here memo of I, and we are not going to do sum or calculation here. We are not going to do sum and calculate. And that's why if we call the complexity, we'll move to what, O of n, because we are not going to do O n square time, because this part, as you can see, that we do not need to calculate because we have already calculated. And that's why the size of the recursion tree can go up to maximum n, and complexity will remain O of n. But when we are talking about space, this will also remain same. Because we are not going this here, but we are going to up to the depth of n, right. And so the space complexity will remain O of n. So now we have another approach, that is the dynamic programming, right. So in this program, in this algorithm, right, as we can see, this problem can be broken into sub problems, and it contains optimal substructure property. Its optimal solution can be constructed efficiently from optimal solution of its sub problem, and we can dynamic programming to do this problem. We can use dynamic programming to solve this problem, correct. One can reach ith step in one of two ways. Either he will take single step, or either he can take two steps, right. I minus one step, I minus two steps. So the total number of ways of ith is equal to the sum of I plus one step and getting from the I plus I minus two steps, you can say, right. So if dp of I denotes the number of ways to reach I step, what will happen? dp of y is equal to dp of I minus 1 and I minus 2. Okay, this is called dp of I. Let's see, we have, this is the memory, right, and we have what, we have 0 1, and from 0 index to from this index to this index, okay, n equal to 5. Okay, so initially if we have 0 and 1, right, next time what happen, we will store this one 0 and 1, we will store at what, position 2, right. Similarly we'll move to what, 1 plus 2, now at index 3 it will be 3. Similarly it will become 5, next 8, next 13. At the n equal to 6, what happened, it is done, right. So if n equal to what, 1, right, so we are at just at one ground, right, we have to take only one step, right, one step, right. If we are talking about like this, we have to take from ground to here only one step, right. we do not need to take extra space. So this will our base case. Okay, now if we'll now we have to take a dp memory of n plus 1, right? So dp of 1 we are taking 1, dp of 2 we are taking 2. dp of 1 means what? We are storing step 1, and dp of 2 we are taking step 2, right? So maximum either I can take step 1 or a step 2, and that's why we are taking step 1 at dp at 1, and dp of 2 we are taking step 2. Okay, if we'll start from I equal to 3, I is less than equal to n, right? The previous, right? We are taking here and here, because dp of 0 we cannot take because it is already 0, and that is no benefit of doing anything, right? This is because this is ground. But when we talk about the step 1, we'll take dp of 1 will take what? Step 1. But dp of 2 will take what? Step 2. From what? From 0. Either from here it will count, it will reach to what? This step, right? 2. But from here to here we cannot go to 2 step. We can take only 1 step. Here taking 1, or here taken we are 2, right? And that's why we are storing dp of 1 and dp of 2 is 2. But from I to 3 will to less than equal to n we are going. Now we will take dp of I minus 1, dp of I minus 2. I minus 1 is what? Is 2. This is dp of 2, this is dp of 2, and this is dp of 1, right? So now we have dp of 3, dp of I, that is 3, I equal to, so that will contain or dp of what? 3, right? And it will be 3, and we have the data on here. So next time when we will come and will calculate the dp of 3, now the dp of 3 will also have data, right? What is 3? Correct, like previously we are doing, right? Next, similarly the loop will continue. Next we will check for the dp of 4, and we will calculate what? dp of 2, 3, and dp of 2, and that will come what? 5. Next when we will calculate 5, then we will take dp of 4 is 5, and dp of 3 equal to 3, and that will be what? 8. And similarly if we will check dp of 6 is dp of 5, that is 8, and dp of 4 equal to what? 5, and that will calculate as what? 13. So in this way we will complete our dynamic programming, and you will see that complexity is what? We will taking single loop. So that's why we are taking O of n, and will move to up to n nodes only, and so that complexity remains same. And similarly for dp of array we are taking dp's array is taking n, and that's why we'll take O of n. Third approach is Fibonacci number, right? So in the last approach, the above approach, we have seen that we have used dp array, right? How? We are taking dp of I minus 1 plus dp of I minus 2 is equal to dp of I, and it can be easily analyzed. dp of I is nothing but ith Fibonacci number, right? So when we are taking n minus 1 Fibonacci n minus 2, and that is called Fibonacci number I of n, right? So now we have just find nth number of Fibonacci series having 1 and 2, their first and second term respectively. So Fibonacci of 1 we are taking 1, Fibonacci of 2 we are taking 2, and similarly we are calculating Fibonacci of n, right? So the function will remain same, right? So we do not need to do taking extra memory for dp to store the data. What we can do? We can do Fibonacci series way, and we can calculate the Fibonacci number, right? So if this is the n, right? So we will take n of n equal to 1, we will return 1. So two variable we are taking, first n equal to what? N, and n equal to 2, right? So n1 and n2, that is first and second, right? And then we will start from I equal to 3 to n, and then we will calculate third, and we will swap the data. First is second, second is third, right? And we will move to second. That we used to do, right? We are taking a what? We used to take n1 equal to what? 1, n2 equal to 2, right? So when we will move, we will take a loop, right? From I equal to 3 to n, right? And in which we used to do n3 equal to n1 plus n2, right? and then we used to do n1 equal to n3, n2, and n2 equal to n3. Similarly, this is doing, and finally we will return the second, and that we will our data. So complexity will remain for what? O of n, right? Because we are moving to nth total n. We're taking single loop, and we're taking 0 to n loop, right? But when we're talking about complexity, we are not taking extra space. That's why it is constant space, right? And that is O of 1. Similarly, we have Bennett method, in which we will do some algorithm things, right? If you want this one, please ping me in the comment box. I'll go through, I'll make this video, and we'll do that. So we have understood the Fibonacci number. This is also another approach in which we see that Fibonacci formula, and we can do, right, in which we have to not do extra thing, only we have to do mathematical things. That is also very easy. So please let me know if you need any other extra weight method to do this to do the coding, and you want to learn. Please ping me in the comment box. I'll go through and I'll explain you. So thank you so much, and please like, share, and subscribe Expert Founder. Thank you so much.